Today we will see about Jacobian matrix. Jacobian matrix. This Jacobian matrix is a very important in a mathematics concept, especially in order to compute the nonlinear system and the linear algorithm in any mathematics as well as in a controller design. So my today's topic is how we're gonna calculate Jacobian matrix in a very simple manner. Suppose that we have a function. Just suppose that we have a function a function f of x is given by minus x1 plus x2 x1, and we have again x2 minus x1 x2. This is in a matrix form. So in order to compute the Jacobian from this function, so how we compute this function, how we find the Jacobian matrix of this function f of x. We'll see solution. If the function is that the Jacobian matrix is in a delta of x, delta dot of x is equivalent to the function or the A matrix A multiplied by the delta x. In another sense, the Jacobian matrix, the partial differential equation of f of x over the partial of x is equivalent to, we have a partial of f of 1 over x1. Again, we have a partial of f1 over partial of x2. Again, we have a partial of f2 divided by x1, partial of f2 over partial of x2. This is the way how we can compute the Jacobian matrix. So this is a basic equation in order to compute the Jacobian function. So don't forget the methodology what I'm represented in here. This is the general equation of Jacobian matrix. So there is no f1 and f2 in this function. So which one is f1, which one is f2? So in order to find, or in order to get the f1 and the f2 function from the above function f of x, which is equivalent to, it is the column matrix f1 of x over this is the first column, and f2 of x is the second column. So we have to find f1. Sorry, this x is not be in here. So f1 and f2 are the function of f of x. So f1 is this function minus x1 plus x2 times x1, and the f2 matrix is x2 minus x1 times x2. So from this we have to compute the generalized equation for this Jacobian matrix. So we have this function. So the partial of f1 of x1 is equivalent to x1. So we have to compute the partial of the function minus x plus x2 x1 over x1. So there is no x2 in here. So for this equation we compute the generalized equation for this. The partial of f1 over f2 is minus 1 plus x1, minus 1 times x2. The second equation, partial of f1 differential partial of x2 is partial of x minus x1 plus x2 x1 over partial of x2 x2, which is equivalent to 2. There is 0, there is 1, so which is x1. So the next thing we have f of 2 over partial of x2. So we have partial of f2 is, our f2 function is here. So x2 minus x1 x2 partial of x2. So we have to compute this. This is 1. So this goes to 1. 1 minus, we have minus x1. So there is the partial of f2 divided by the partial with respect to x2. So partial differential equation of f2 with respect to x2. This is f1 respect to x2. This is f1 with respect to x1. So we have two estimations. The first one is estimating f1 function with respect to x1 and x2. The second is f2 with respect to x2. Sorry, it is x2 with x2 and x1. So the second thing is the partial of f of f2 with respect to x1. So we have to calculate this, which is x1 again, which is partial of x2, which is x1 is cancelled out. There is minus x1. So minus x1 is minus 1, so which is x2. So we have those functions, as you can see from the formula or from the equation. The partial of f of x with respect to, this is the generalized equation for the Jacobian matrix, as you can see from the equation. Our f1 partial of f1 with respect to x1 is minus 1 plus x2. Partial of f1 with respect to x2 is x1. Partial of f2 with respect to x1 is minus x2. And partial of f2 with respect to x2 is 1 minus x2. So from this, the partial of f of x with respect to x is now the finally the computer equation. Our f1 is minus 1 minus x2. The second f1 with respect to x2 is, which is x2. No, sorry, x1. There is x1. Again, the second f1 with respect to f1 is minus x2. And we have partial of f2 with respect to x2 is minus 1 minus, no, 1 minus x1. So there is the Jacobian estimation, or the Jacobian form of the function f of x is this, and the generalized Jacobian equation is this one, which is 1 by 1 n by n row matrix. So this is, as you can see, this is a 2 by 2 matrix, by the way, n by n by n matrix, which is 2 by 2 matrix from the first function f1 and f2. So just to generalize that, for any equation we need to have a Jacobian form, especially for computing the controller algorithm, let's say, in order to calculate the Jacobian matrix for the linearized form of the nonlinear equation. So system is, we have a nonlinear equation or nonlinear plant is always linearized into linear form. So in order to compute that, the the Jacobian matrix or the linearized form. By the way, the another name for this linearized form, I mean the Jacobian matrix, is Jacobian matrix. Matrix is said to be like a linearized form of a given matrix. So in today's presentation, I have to share you the Jacobian matrix of a given equation. So this is a function. So suppose you are exposed to find the Jacobian form of the function. So if the function is f of x, the Jacobian matrix is in a minus 1, minus x2. This is the a1, let's say, x1 minus x2, 1 minus x2, which is n by n matrix. This is the generalized form of Jacobian matrix. In the next episode, I'm gonna show you the I will show you the linearized form of the Jacobian matrix, especially in order to make the nonlinear plant into linear form. We need to compute the Jacobian matrix as well as the again values lambda 1 versus lambda 2 at a given point x is equivalent to 0 0, which is at the equilibrium point, as well as x is from 0 to some point of infinity. So we have to calculate the eigenvalue, and in order to solve the state trajectory or the state phase at x1 and x2 at x1 and x2, in order to estimate, or in order to guarantee to know the trajectory, whether the function is stable, not stable, or a saddle point. So to do that, we have to know that the eigenvalue and eigenvector estimation, the Jacobian matrix, and finally we have to know about the linearized form of a given matrix. So this all about my today presentation to all of you, my you guys in all over the planet of the earth. So thank you. If you like, don't forget subscribe, share, and like my YouTube channel. Thanks.